Welcome back to the gas laws chapter. What we're going to cover this time is basically the bread and butter of this chapter, the bread and butter of everything you need to know in terms of how can I use the gas laws and what way will it benefit me the most to know from this, all right? So, and we have worked with this before, and it's PIVNERT. Again, PIVNERT is called the ideal gas law. And we really need to know how to use this from beginning to end, from front to back, from top to bottom. No matter what we're doing, we want to be able to manipulate this formula and be able to work with it in any way possible they can ask us. All right. So that is our goal for this entire thing. So let's talk about what PIVNERT stands for, what it means, how it works, and kind of go from there. So that is our goal for this particular lecture series, is to go through as much ideal gas laws, examples and problems as we possibly can, so you can kind of get an idea behind it. Now, I hope that you can recognize several things. I hope the first thing you can recognize is what P stands for. Well, P is for pressure. However, you've got to realize that when you're dealing with PIVNERT, or the ideal gas law, that it must always be in atmospheres when we're talking about pressure. V, it stands for volume. But you've got to also realize that it must always be in liters. All right, that's number 2. N. N stands for moles. But here is the problem. We all probably realize that moles is very rarely given. So it's going to be given normally in one of two ways. So it's normally given in two ways. And again, you can write it above it, you can write it up beside it. The first way it's going to be given is the mass. Well, how do you get moles from a mass? Well, that's your gram to mole conversion. All right, so that's the first thing you're going to have to do, is basically you're going to divide by the molar mass. All right, that will give you number of moles. The second way you're going to need to be able to figure this is they're actually going to give you the molarity. All right, so that is the second way that can get it to you. Well, how do you get moles from molarity? Well, they must also have to give you a volume. So in that case, what you would do is you would do molarity times volume, with the molarity times liters, and that will give you a number of moles. So it is very rarely that they just plot down your number of moles and go from there. You're probably going to normally have to convert those two. Now, the last lecture, it's in lecture 2, I mentioned this R thing, this R constant value. This is called the proportionality constant, or what I like to refer as the gas R. This is the number you need to memorize. It is 0.0821, and this is the part where you're going to mess up again. The numerical value, 0.0821 liters times atmospheres over mole times Kelvin. The way I like to say is Latam over Molk. Again, it's just an easy way to remember it. Latam over Molk is the best way to remember that. I need you to understand that this thing right here, this R, is on the, excuse me, I just completely had a mental moment. It's on your equation sheet that you actually get on the exam. If you somehow or for some reason forget the number or forget the units, please refer back to the equation sheet. But there is one issue. There is one issue here, and the fact that on the equation sheet they actually have 3 R's listed. You've got to be intelligent enough to know that you need the 0.0821. And let's think about that for a second. If you're using PIVNERT, remember that your pressure must be in atmospheres, your volume must be in liters. Well, look exactly what your top unit is in your unit for the R value. It's liters times atmospheres. That should give you a good indication of which R to use. Now, the other R, and again, hopefully you know this is your energy R, is 8.31 joules per mole. All right, again. So you should realize real quick that if you try to use this number, it's not going to work. The reason why is, again, we need atmospheres and liters. What is joules? Well, joules is an energy constant. It's an energy unit. So we can't use this value. The other one that they actually give you is 62.36. Let me just kind of show you what it's. Again, it's 62.36, and it's liters times torr over mole. And I'm going to be honest with you. In all of my years of chemistry, I have never, ever, ever, ever seen this number used or used it myself. So I honestly don't even know why they give you that value. So completely ignore that one. You're never going to have to use it, okay? All right, so that's the next thing. And then finally, T, you better know that your temperature must always, 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 always be in kelvins, okay? So, and be quite honest with you, it's normally given in Celsius, okay? So you're going to have to convert it. And if you forget, again, normally in Celsius. And so K is equal to C plus 273. So again, that is a number that you're definitely going to have to memorize to be able to convert it. All right. Now, some of you may care, some of you may not care, but I want to show you this, and it's how in the world did they come up with this 0.0821. I do also want to mention this is the number that I use on the actual equation sheet. It's 0.08206. This is the number, again, that's on the equation sheet. You can use this number, the longer version, or you can use the 0.0821. I like the 0.0821, and again, you could just tell that that 6 makes that 0 round up to 1. That's your only difference there, okay? So if you do forget it, it's okay to use that number. There's not any difference there. But I want to show you something. I want to show you where this R thing comes from. So let's talk about that for a second. Excuse me, let me start over. So we have PV equals nRT. And what I want to do is I want to algebraically solve for R. All right. So if we algebraically solve for R, you know we divide both sides by NT. So we're going to have PV over RT. And so let's just assume that everything we have is at STP. This is something that you need to go back and look at. Make sure you know what STP is, what the values are. STP is a standard temperature and pressure. Do remember that, okay? Excuse me there. So what STP, if you plug all your values in for your STP, the pressure you should know is 1 atmosphere. And you tell me this, how many moles are there at STP? You know what? I completely just messed this up. Excuse me. I need to erase this. It is not RT, but NT. My apologies there, okay? So volume, we know it's 1 liter. And this is the part I was getting to, and it kind of threw me off when I started looking at it. The number of moles. Remember, if we have, you know what, I tell you what, let me completely start over. I have completely messed this part up, and I knew what I was doing was wrong when I started. All right, my apologies here. All right, let's try this again. At STP, we know that there is a relationship. 1 mole takes up how many liters? This is the part I was trying to get to. My apologies. So 22.4 liters. This is the key that we're trying to get to, all right? So that is the number we're going to plug into our volume. So 22.4 liters. And again, this is in 1 mole. And what was your temperature? Remember, this is the one that threw everybody off, that messes everything up. You know, normal standard conditions, it's 25 degrees Celsius, so it's 298 Kelvin. But remember, at STP, it's going to be 0 degrees Celsius. And so, in that case, it's going to be 273 Kelvin, okay? So that is the biggest change here. So 273 Kelvin. Now, I'm not going to do this for you because I can't prove it to you, but this is what I need you to do. I need you to take those numbers and plug them in and divide. So do 22.4 divided by 273, and I will guarantee you that the number you come up with is 0.0821. So this is where the 0.0821 comes from. It's basically a rearrangement of your ideal gas law, Pivnert, and solving for the variable R when you are at STP. All right, so that's where the numerical value does come from, and I did want to show you that, okay? All right, so moving on. So let's look at our first problem here. I'll tell you what, let's look at this first. The mole box, this is just something to just kind of keep in mind. Again, I showed you this for a reason, and I do want to reiterate. Remember, Avogadro's law. This is what we talked about last time. Equal volumes of gases. So again, let's just pretend this box right here. This is our box. That box has a volume of all gases. The key there is all. It does not matter what gas, nitrogen, helium, hydrogen, carbon dioxide, whatever it is, at the same temperature and pressure, and this is the key, remember, contain the same number of molecules. All right, that's the key there. And if we do have your STP standard temperatures, If we have a box that's 22.4 liters, then we know we'll have 1 mole in that box. Okay, very important to remember that relationship. This is another YouTube video. Again, I don't have the ability to show it to you. It's called the ideal gas law. If you'll just look it up, it should come up pretty interesting. All right, so here's our first example of using the gas laws, or ideal gas law. A sample of hydrogen gas has a volume of, all right, so they have just given us V. But remember, what do we always want our units in volume? Liters. Good. This is going to be easy. At a temperature of 0 Celsius, all right, well, it's given us 0. Well, we know we don't want that, so let's just go ahead and convert it to Kelvin. So let's say that's 273 Kelvin, and the pressure of 1.5 atm. All right, we know this is a pressure. They've given us atms. That's a good thing. My apologies, I did not mean to do that. Okay, so again, this is a pressure, and it's in the unit we need. Calculate the moles of H2 molecules present in the gas. Now, we know that moles is going to be our N value. All right, so the law, again, so they've given us a pressure, a volume, a temperature, and they ask for moles. I'm going to tell you, on the AP exam, they're not going to say, hey, use the ideal gas law. They're not going to do that. So you've got to read through this and determine what exactly do I need to do. Again, they've given you pressure, a temperature, a volume, and they ask for moles. Well, the only thing logical here is to use Pivnert. All right, so this is our Pivnert law, and they're asking for N, so let's rearrange it for N. So N is going to equal PV over RT. All right, so we know our pressure, so let's plug our pressure in. It's going to be 1.5 atms. Okay, we know our volume is 8.56 liters. Okay, now R, again, it's a constant, and just because I'm writing on an iPad and things are a little bit difficult for me to do this, I do want you to just make sure that you write the units for R. They do look for that. And again, it may be really hard for me to kind of make it clear here, but I'm doing the best I can. That is your R, and then of course make sure your temperature. Make sure you use the 273 and not the 0. Again, anything divided by 0 is not possible, so that should be your red flag automatically. All right, so you plug these numbers in, you plug them into your calculator. Now, there's one thing I do want to make mention of. Sig figs. Really, really, really important that you use the correct sig figs. They give us 0, but again, we don't ever really want to use 0 here. So we're just going to say 273 is 3 sig figs. You never count a constant in terms of sig figs. So there's 2 sig figs in 1.5, and there's 3 in 8.56. So my least number of sig figs is 2. So my answer needs to be 2 sig figs. So the correct answer here is 0.57. So 0.57. Now, is that 0.57 millimeters, inches, joules? What is it? You've got to give the answer in terms of what they were asking, and it's moles of H2. All right, and so that is your correct answer for that particular question. All right, so hopefully that was easy enough. Moving on to the next one. Suppose we have a sample of ammonia gas with a volume of, all right, so they've given us a V. All right, and it's in liters, which is a good thing. A pressure of 1.68 atmospheres, so they've given us a P. Then it says the gas is compressed. Well, let's talk about that. What does compressed mean? That means it is made into a smaller space. So notice what they did. They give us a volume again, and then it says at a constant temperature. Use the ideal gas law to calculate the final pressure. Now, I'm going to be honest with you guys. This is not the time to use the ideal gas law. And this is in this particular section for a reason. However, it's not the best location for this question. And here's the reason. Notice what they've given us. They've given us one V. They've given us one P. They've given us another V. And then they said calculate another P. Well, we should know that that is one of our other gas laws, one of our Boyle's, Gay-Lussac's, or Charles. Which law will this one be under since it says a constant temperature? You said Boyle's, very good. So since it's at a constant temperature, your T's are going to go away. So remember, Boyle's law was P1V1 equals P2V2. And guys, the ones and twos are arbitrary. It does not matter which one you pick. I always like to say 1 is my initial and 2 is my final. And so notice what they ask you for. They ask you actually for the final pressure. So that's what we're gonna solve for P2 here. All right, so P2 equals V1. Excuse me, I inverted those. It doesn't matter. So V1 P1 over V2. And again, all of our units are in good units. So our volume is 3.5 liters times 1.68 ATMs, all divided by a 1.35 liters. Now, remember, go back to sig figs here. Very important in terms of sig figs. We have 2 there, we have 3 there, we have 3 there. So we're going to go with our least, which is 2. So the answer is 4.4 liters will cancel, leaving us with atmospheres. And so it is atmospheres of NH3. And I know what you're thinking, where did you get NH3 from? Suppose we have a sample of ammonia gas. So that's where that's going to come from, okay? All right, so hopefully that helps. Now I'm going to move on to the next one. And guys, let's just be honest, you can read through this one, but here's the deal. I'm going to go ahead and tell you this. It is at a constant, excuse me, let's go back. It says it is at a constant pressure. What law states constant pressure? Hopefully you said Charles. Now, remember, this is your V's and T's, but there's something I need you to remember. And I'm not going to do any of the number values here, but there is something I want you to remember. This is your tricky T area. Please do not forget it's V1T2 equals V2T1. Take these numbers, plug them in, and go. But there's one other thing I need to remind you. What is wrong with that number and that number? Hopefully you figured that out. I will tell you the answer is 4.9 liters. Work it out. See if you make sure you get the right answer there, okay? Moving on. This time, again, this is kind of out of the box as well. This is the one that's going to kind of throw us off too. It's not a PIVNERT question, but I want to show you how we can get some information out of this. And again, I do need to apologize. So I should have moved these around. A sample of diborane gas, which is V2H6, a substance that bursts into flames when exposed to air. It's kind of a scary idea. Has a pressure of 345 torr. All right. Well, torr is not what we really want, but let's see if we can work with it. All right. So we have a P at a temperature of negative 15 degrees Celsius. All right. We know we got to get rid of that, so we're going to add 273 to that, which actually turns it into 258. All right. And a volume of 3.48 liters. All right, so they give us a V. So far we have a P, a T, and a V. If the conditions are changed so that the temperature is 36 degrees Celsius, all right, well, we know that's Celsius, so we need to get rid of it. So that is now going to be 309 Kelvin. Again, all I'm doing is adding 273 to it. And the pressure has changed to 468 torr. All right, let's talk about this for just a minute while I'm on it. They give you torr, and they give you torr again. Well, I know what you're thinking. Well, don't we have to convert that to atmospheres? Well, here's the issue. And I'm just going to go ahead and tell you that these torrs numerically are going to cancel, so you don't have to alter them to atmospheres. So if they ever cancel, you don't need them. But I will tell you this: if you are ever using PIVNERT, you will definitely have to change them over, okay? So please do not forget to change them if you're using PIVNERT. And then the question is, what will the new volume be? All right, well, they've given us they've given us 2 P's, 2 T's, and 1 V, and they've asked for another V. Well, this is just your combined gas law, all right? So this is P1, V1, and then T what? Hopefully you said T2, because your tricky T's here. And so then you have P2, V2, and then T1. And again, what will the new volume be? So we're going to solve for V2. All right, so V2 is P1, V1, T2, all over P2, T1. Now, you can take your numbers that are given in the problem and plug them in, but remember, this is very important. This 309 is T2. Please make sure you plug it into the top. And this 258 is T1. Please make sure you plug it into the bottom down there. I'm going to go ahead and give you the answer so you can make sure you get it correct. It is 3.07 liters. So make sure you solve it and make sure you get the right answer there, okay? All right, moving on. All right, so let's look at this one. This is one of those other problems that you really don't need the ideal gas law for it either. What you essentially need is the combined gas law again. And it says calculate the change in volume. So just solve for V2 again and move on from there, okay? And again, so my apologies on all that. I really need to rearrange these. This is the first time I've worked with this PowerPoint presentation since I've added some things and changed them around. So I do see some places where I could make it more efficient. All right, gas stoichiometry. Use Pivnert to solve for the volume. Now notice what it says, solve for the volume. So let's go ahead and rearrange this. So we're going to be solving for V. All right, so we're going to divide each side by P, which makes it nRT over P. All right, so this is our math, or this is our formula of 1 mole. All right, so we know that we're going to have 1 mole. All right, we know R is always going to be constant, and it's 0.0821 liters times atmospheres over mole times Kelvin, or Latin over mole. All right, and then your temperature. We don't know it yet, or we don't know our pressure yet, but then look what it tells us. At STP. All right, well, we know our temperature at STP is going to be 273 Kelvin. And we know our pressure is going to be 1 atm. So the math here is real simple. It's just 273 times 0.0821. And here's the magical part. Hopefully you looked at this and said, wait a minute. The volume of a gas for 1 mole at STP, isn't that the constant we've always been talking about? Yes. The answer is 22.4 liters. So this is where that came from. So now I'm just kind of showing you mathematically how this number was derived and how it was determined and where it came from, okay? So again, does this look familiar? Yes. The molar volume of a gas at STP is 22.4, and this is where it came from. It came from the stoichiometry problems and allows us to work things much, 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 much faster. So again, so hopefully this maybe proves that point, okay? Again, this is kind of what I was just telling you, so does it look familiar? Yes, it's the molar volume, so you can kind of read through that. All right, gas stoichiometry number 1. All right, if the reactants and the products are at the same conditions in temperature and pressure, then the mole ratio of gases are also volume ratios. Notice she said, huh? Say that again? If reactants and products are at the same conditions of temperature and pressure, then the mole ratios, I know what you're thinking, what do you mean by mole ratios? Where does that come from? Essentially, this comes from your coefficients. All this is the mole to mole ratio, guys. Nothing harder, nothing simpler. So the mole ratio, and again, I underline gases for a reason because this is gas stoichiometry, are also, notice what it says, volume ratios. So what do I mean? What I mean is if I have a balanced equation, this is, again, hopefully you recognize this, maybe, depending on when you're watching this video. This is the Haber-Bosch process. Remember how we talked about the production of ammonia gas is the Haber-Bosch? So we have 3 moles of H2, and again, where did the 3 come from? It's the coefficient. 1 mole of N2, come from the coefficient, and 2 moles of NH3, and again, that came from the coefficient. So read it now one more time. If the reactants and products are at the same temperature and pressure, then their mole ratios are also volume ratios. So essentially what we're saying is that 3 moles of hydrogen gas will take up 3 liters, the 1 mole of nitrogen will take up 1 liter, and the 2 moles of ammonia will take up 2 liters. Is essentially kind of how we're relating this. But notice, one more time, what it's referring to is gases. All of these must be gases. If they're not gases, it will not work this way. All right, so here's the question. How many liters of ammonia can be produced when 12 liters of hydrogen react with excess nitrogen? Well, the good news is they just told us something key. They told us that you have excess nitrogen. So essentially, we can kind of wipe that away. Okay, so we can get rid of this nitrogen because it is in excess, which makes hydrogen the limiting reactant. So they're wanting to know how many liters of this stuff can we make? I know what you're thinking. How can you go liters to liters? What is that all about? Remember, gases have a liter-to-liter ratio just like the mole-to-mole ratio. Okay, so we're going to start with 12 liters of hydrogen gas, treat it just like a mole-to-mole. So what is your top-to-bottom ratio from hydrogen to ammonium? It is a 3-to-2 ratio, so as we go through this, it's 3-to-2, which gives you 8 liters of ammonia. So again, if you start out with 12 liters of hydrogen gas, you're going to end up with 8 liters of ammonia gas. All right, here's another one. How many liters of oxygen gas? Notice what it says at STP. The reason they tell you it's at STP is that way you know that it's at the same standard temperatures and pressure. Can be collected from the complete decomposition of 50 grams of potassium chlorate. Uh-oh. They have already made us aggravated with the way they're asking this question. And here's why. Because they've given us grams of potassium chlorate, which is this thing, all right? So let's see what we have here. We have 50 grams of potassium chlorate, and we need to know how many liters, hope it doesn't change. All right, so again, we're asking for liters of oxygen. So essentially what we're doing is we're going from 50 grams of this stuff to liters of that. All right, so how can we relate this? So again, we know first of all we got to get rid of the grams, we got to go to moles. So that is our first major step. So again, the molar mass of potassium chlorate is 122.55 grams. All right, so now we're at moles of KClO3. So essentially what we need to do is we need to go from a mole to liter ratio, which is a mole to mole as well. So it's 2 moles of KClO3 to 3 moles of O2. And again, all this is coming from the coefficients of the balanced equation. The 2 is here. The 3 came from here. That's where that came from. All right. And then liters. This is the part that they're going to get you right here. You are going to forget this aspect. So now, how important is this STP thing? And I've told you a million times, you have to know that relationship. That at 1 mole of a gas at STP, there are 22.4 liters. This is why I'm showing you this. It's very important that you grasp this and understand this and can manipulate all of these things, okay? All right, and the cancels, which ends up giving you 13.7. Again, that's kind of a typo down there at the bottom. It is 13.7 liters of oxygen. All right, let's see. Now, this time they've changed it up a little bit. How many liters of oxygen at 37 degrees Celsius? Well, that is a problem all within itself. What is the problem with that with this question? Well, the reason there's a problem is because it's no longer at STP. So the relationship of 1 mole at STP equals 22.4 liters, we can no longer do. This relationship is out. So we've got to do something else. How many liters of O2 can be collected at 37 degrees Celsius? Again, we need to change that to Kelvin, so you can go ahead and change that. At 0.93 atmospheres can be collected from a complete dissociation of 50 grams. So now let's start over with what we have. So now, clear the board. We know we need to go from grams to moles, just like we did last time. And then we need to go to moles of O2. So notice what they have done. They have solved for the moles of O2. All right, well, let's think. If we get moles of O2, that's going to give me N. I have a T. I have a P. And they're asking for a V. Well, no, that makes sense. That means I need to use Pivnert. Exactly. So that's exactly what you're going to have to do. You're going from one compound to the one that's desired, but the only thing you're going to be able to get is your moles of O2. Well, then once you get the moles, notice what the question is asking you for. The question is asking you for liters. Well, that's when Pivnert will come into play. All right? So that's going to give you 0.612 moles of oxygen. Again, this is your N value. And then you're going to use your Pivnert. All right, so that's our goal. Use PivNert from this point. Well, we know that volume is N over RT. Excuse me, V equals nRT over P. And so you just plug in everything they've given you. Just make sure. The key here is make sure you get this change right here. Make sure you change your temperature. That's the one that's going to throw you off. Okay? And again, of course, your moles just came from what you saw for. So if you'll notice, all this is a gram to mole conversion. And then once you have your moles, you're then going to have to be able to use PivNert in order to find your volume. Very, very, very important. Now, would it have been much nicer had everything been at STP? Yeah, well then we could have just used the 22.4 liters in 1 mole and been done using stoichiometry. But we are going to have to use PivNert because it's not at STP. All right, which ends up giving you 16.7 liters. All right, hopefully that makes sense. All right, so a sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of nitrogen are present? I really, really pray that you can do this one. It says has a volume of that, excuse me, let me go back, has a volume of 1.75 liters at STP, and then it asks for moles. Well, what do we know about moles and liters in STP? Well, at 1.75 liters, we know liters is going to have to go on bottom. And do we have a direct conversion to moles from liters at STP? If you say no at this point, I don't know what to do. So we have 1 mole and we have 22.4 liters. And I told you, and I've been begging you forever this entire time to please commit to memorizing that. All right, so this is where you're going to have to use it. And the correct answer actually comes out to be 0.0781 moles of N2. And that is the correct answer for that one. Let's look at the next one. Quicklime, which is basically just calcium oxide, is produced by thermal decomposition of calcium carbonate, CaCO3. All right, calculate the volume of CO2. So notice what they said. We are going to want the volume of CO2. Yay, yay, yay. They have given us something great here. At STP, produced from the decomposition of 152 grams of calcium carbonate by the reaction. All right, so we have been given 152 grams of this stuff. And they're asking about the volume of CO2. All right, well, let's figure this out. This is basically just like something you did earlier. So we have 152 grams. Now, to be able to go from CaCO3 to CO2, what are we definitely going to need? The only way to compare two different compounds, hopefully you've set a mole-to-mole ratio. Well, we have grams. We're definitely going to have to get the moles first. All right, so grams is going to go on bottom. I've got to have moles. Now, I'm going to be nice, and I'm going to give you the molar mass of calcium carbonate. The molar mass in 1 mole is 100 grams on the dot. Again, you can double check me, but it's 100 grams on the dot. So now we're at moles, and again, this is of CaCO3. So now we need our mole-to-mole relationship. So we're going to moles of CO2, and this is CaCO3. So what is our mole-to-mole ratio here? Well, let's double check and just make sure it's balanced first. We have 1 Ca, 1 Ca, 1 C, 1 C, 3 O's, 1 plus 2 is 3. So it's a 1-to-1 ratio. All right, well, here's the deal. Since it is at STP, we don't have to stop right here. We can actually go one more step. We can go in moles of CO2, we can go straight to liters of CO2. And why are we allowed to do that? Again, this is the relationship you have to know. In 1 mole, we have 22.4 liters. Again, 1 mole, we have 22.4 liters of carbon dioxide. So if you run through this calculation, you will determine that the answer is 34.0 liters of carbon dioxide. Again, hopefully this is making sense. Hopefully you're kind of understanding it. It's not too difficult. It's a very simple way to approach some of these questions. All right. Let's move on to the next one. We're going to do about 2 or 3 more slides here before we shut this one down. All right. This was going to be long and drawn out, but just stay with me, okay? Just stay with me on this. A sample of methane gas having a volume of 2.8 liters at 25 degrees Celsius and 1.65 atmospheres was mixed. All right. Well, this is the problem so far. So let's go ahead. Excuse me. Let's go ahead and get rid of that temperature because we know we got to change it anyway. So we're going to need 298 there. That's 298 Kelvin. Was mixed. All right. This is very important here. Was mixed with a sample of oxygen gas having a volume of 35.0 liters at 31 degrees Celsius. All right, let's go ahead and change that. That temperature is going to be 304 Kelvin. Again, 304. 304 K. And 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. So we already know that we're going to need a reaction for this, but just because of the way it's worded. All right, so CH4 plus O2 yields CO2 and water. Now, hopefully you recognize this as a combustion reaction. That's my goal for you to be able to recognize this. And it is not balanced, so we're definitely going to need to balance it. But it's actually 1, 2, 1, 2, real simple, real quick to balance, okay? And then the question is, calculate the volume of CO2 that was formed. But here's the crazy part. Then they completely change everything else up on you. Now, let's be honest. There is a lot going on here, so I need to kind of help you through this. The first issue is they have given you some information about methane. They have also given you some information about oxygen. And then they ask you about one of the products. What do you have to do here? And I'm trying to get this out of you. I'm trying to get you to see what's going on. They have given you 2 reactant amounts and then ask you about one of the products. If you said you got to find the limiting reactant, fantastic, great, awesome, well done. All right, so that's what you're going to have to do first. But the problem is they give you a volume, a pressure, and a temperature. Well, that doesn't make any sense at all right? So what we're going to have to do is we're going to have to be able to determine the limiting reactant. That's our first goal. Now, the limiting reactant we know is LR is the number of moles divided by the coefficient. All right. Now, due to time's sake, I want to kind of cut this video short, but here's what I'll need you to do. Show this, set this up. Use PivNert and the data they gave you for methane, which is all right here, and plug that in to PivNert and solve for M. That's going to give you your moles. And then take the information they gave you about oxygen, which is all right here, plug that into PivNert and solve for M. And that's going to give you your number of moles. And that's where I'm going to start. Okay, that's where I'm going to go ahead and jump in right here. So we have CH4, and the number of moles that was achieved was 0.189 moles. That's 0.189 moles. Now, the coefficient for this was 1, so it's not going to change. But O2 was 1.75 moles. All right, and we need to divide that by 2. Why am I dividing it by 2? Again, the 2 is your coefficient. Well, when you divide it by 2, it actually comes out to be equal to 0.875. Well, as soon as you see this, you know that this is now your limiting reactant. Methane is your limiting reactant, okay? So that's what you're going to have to do. All right? Methane's your limiting reactant because it is the least amount. Well, now if we go back to this, here's the issue. We now know to pick the limiting reactant to go to carbon dioxide. All right? So what we're needing there is a mole to mole. Well, notice what you have. The mole to mole is a 1 to 1. So what we're getting at is that your 0.189 moles of CH4 is equal to the moles of CO2. Again, why? Because it was a 1-to-1 mole-to-mole ratio. All right, so now we have our number of moles of CO2. Let's go back and look at the question. Again, there's a lot going on here. Here's the question. Calculate the volume of CO2. The volume of CO2 at this pressure and this temperature. This is, again, why this is a long, drawn-out problem. This will be a very, very multi-step problem in a free response. So now we need the volume of CO2, and we're going to use Pivner, which is nRT over P. Well, you know your moles, you just solved it, was 0.189. You know R is a constant. You know T, change that from 125. We need to change that to 398 Kelvin. All right, and then your P is 2.5 atmospheres. And if you plug all that in, the final answer, again, I'm cutting this short, I know I'm kind of moving a little fast, is 2.47 liters. All right. Again, if that was a little too fast for you, go back, double check, see what was going on, and from this point, we are going to stop, and we will pick up with session 4 next time. Thank you for watching.